Hi guys, welcome to another Learning Electronics Repair video. This video is sponsored by PCBWay, who very kindly sent me a t-shirt, by the way. Thank you very much, PCBWay, much appreciated. I guess you want to know what's on the back of it, don't you? Can you see? I hope it comes up on the camera alright. Yeah. So, what I want to do today is build a cheap electronic load, an active load. So we can use this to test power supplies. In particular, I'd like to test ATX power supplies, but we can use this to test anything where we effectively need a load. This is a project from PCBWay's shared project section. So this has been uploaded by the author. And when I bought these PCBs, which cost me $5, the author gets a commission from that. So this, and I hope some of you guys are considering it now, is a very good way to make yourself a little bit of money from your own projects without having to actually buy and stock any of the PCBs. Yeah, people order them direct from PCBWay, you get a commission. So I'll just show you the project we want to build. And then let's have a look to see how useful this is. This is the project on PCBWay. They have lots and lots of projects. If any of you guys are interested to look through some of these, if you spot anything you'd like me to build on the channel, then let me know and I will get the PCBs ordered. PCBWay are kindly sponsoring the channel, so that actually doesn't cost anything and we can make lots and lots of interesting things. But this one definitely is today's project. The original video is on YouTube. I will link it from this one. It is in Russian language. No, I tell a lie. This guy is Ukrainian, so I don't know the language well enough to know which he's speaking. I will be honest with you. But we have some information here on the Google Drive. So let's go to the Google Drive and see what we have. And there we have a schematic. So basically the components in this are fairly commonplace. There's nothing particularly unusual. I will download the schematic and then we can open it up a little bit bigger, I think, and we can actually have a look. In fact, I have it here already. So let's open it on our computer and let's see what we have. This area of the circuit with this switch, and I don't know what this is saying in Russian, but, or Ukrainian, I apologise, somebody's going to tell me which is right and which is wrong. But this switch appears to select either the voltage from the 12 volt regulator into this resistor network, which is variable, or it selects the voltage from the power supply you are connecting to the load, which is here. Now this part of the circuit, so this is your 12 volts coming in from the independent supply, goes through another resistor network here. We have this transistor, and you can see the transistor is connected from this point to ground. So when this transistor is switched on, it will effectively ground this end of this resistor, which basically means the voltage here drops to 0 or close to 0. We can see that's coming into this op amp here, okay, on one of the inputs. And the way this transistor is switching on is via the base, so it needs a voltage on the base to turn on. Now, that voltage looks like it comes through this resistor from the input power supply, but it can also come from here. So this op amp, which is switching the fan on or off, if we think about it, to switch the fan on, we need to put the voltage on the base here of this transistor to turn it on. Okay, the fan is powered from the 12 volt supply, you can see that. So the voltage here goes up to turn the fan on, and that voltage, when it gets above, well, the 5 volt zenith plus another diode 0.6 of a volt drop. So when it gets above around 5.6 volts, it puts voltage on here. So when it reaches about 6 volts on here, coming from here, that's also can turn this transistor on. So it looks like this transistor can be turned on either via this resistor or via this. I suspect this might be some sort of biasing and maybe isn't enough to switch this on initially. We'll have to have a look around it when we've built it, I'm not sure exactly. But switching this transistor on, we'll take the input of here low. The other input is coming from the variable resistor. And this transistor, when the input of this goes low, I'm guessing this transistor turns on and grounds the voltage here. So I think, just looking at it, this could be effectively a circuit so that when the fan turns on, it switches the load off. I'm not quite sure. But we can have an investigation of it when we've built it. We can measure around this. I have no circuit description for this. And I'm not a designer. I'm just sort of thinking how it might work. So we can have a look around that and try and figure out exactly what that does. But it looks like it's something like that. Okay. The output stage of this, we have the 4 op amps, and this will basically be like a comparator. So it's effectively measuring, if you look, this is a 0.05 ohm resistor, and it's measuring the voltage across there, which will depend on the current, and comparing it with the voltage on here, which will depend on the setting of this and what this transistor is doing. So that is going to be a constant current source. When you reach a certain amount of current, you'll have a certain voltage across this resistor, okay? And that then effectively starts to back the transistor off so it's not conducting as much. I'm sure that effectively is a constant current source. The op amp drives this transistor, BD139, and that effectively amplifies the signal and drives this transistor, the D209. This is a large output transistor. And you can see you've got 1, 2, 3, 4 of these circuits all in parallel. This load can apparently, with the correct cooling, handle up to 300 watts. So at that point, each of these output stages, if you like, in parallel, would be handling 75 watts each. So that's what we have. I can sort of see how this will work, which is good. If it doesn't work, we can hopefully diagnose what the problem is. So, get into the comments below and tell me where I was wrong, which is fine because I'm not the designer, I'm the fixer, yeah? And B, let's start putting it together. The only thing special about this circuit really is the cooling on the output stage. These resistors, which are shown as zigzags rather than squares, these are power resistors, yeah? I don't know what wattage they are. I'll show you them on the video in a minute. I think they might be around 10 watts each. And these components, which are in red, 100k, I think are critical values. We need to measure some and get the ones closest to the value we want, because those effectively set the voltage on this input and they work with the voltage on the current sensing resistor. So I think these must be the correct value, each the same, so that all the output transistors turn on and off at the same point. You don't end up with a situation where one is doing all the work and the other ones aren't quite switched on, because obviously all the current would flow through one transistor. So that's how I see that. We have a little bit more information here. So it's saying we can smoothly set the required current, the load current, to test any power supply. Maximum current is 10 to 15 amps. Power can reach 300 watts. Electronic loaders overload protection. Smooth control of the level of current consumption. Temperature control and protection against overheating. So we can pretty much figure out what that NTC is doing. Overload protection, I'm pretty sure, is part of that circuit we were just looking at, where I said it could shut down. And it's basically saying that we don't need to use power resistors or incandescent lamps anymore. We can just set the current. This is the YouTube video, which as I said, I will link. And if we have a look at the project, I'll just pause it here. Oh, well, I didn't want that to come up. I just wanted it to pause. Let's get rid of that. Okay. So we can see these are the power resistors. Okay. I'm not quite sure what this is here. This is where the load's connected. Yeah, these screw terminals are actually going to the output transistors, and I think he does show us somewhere the transistors on an external heatsink. Let me see if I can find it. Yeah, so those are the output transistors. This is the driver transistor. So we get some idea of how this thing is put together. And then look, he's using a CPU cooling fan, some sort of heatsink. Okay. We have connected to this a variable. Yep, there's a potentiometer. That's for adjusting the current setting. Okay, so we can see from this a good idea of what we need to do to put this together. Certainly enough to start building it. Okay. The actual intention is to build 3 of these into one unit, and then we can use them to load an ATX power supply. So 3.3 volts, 5 volts and 12 volts. And I'm going to add some current and voltage meters to the project as well. But I think the whole project, we can price it up in the end. But I suspect each of the electronic loads will be less than €20. This might be a sort of a 40 or 50, 60 euro project to build for the triple channel load that in theory could handle up to 900 watts. We will yet have to wait and see if that is the case. But considering the cost of commercial units, this is actually pretty good, quite cheap. We can have a look at the cost of actually building these. So if I just go into my orders, you can see I had to order some of the components. Just go down a little bit. Okay. So from here, LM324s, I only need 1 for each board. I ordered 10, total cost €1.51. This is with postage. The output transistors, I actually used the same one he's using, D209, but the one he was using, the designer, had the TO3 metal can type. I've used the flat pack type, the TO3P. They should have basically the same wattage dissipation, and they're going to be a lot easier to mount onto the heatsink. So that's why I ordered those. You can see I ordered 20 of them, 2 packs of 10. Which came to €7.38. This is the most expensive part, really. I actually need 4 for each one, so I need to use 12. I ordered 20. Okay, so that's quite a few spare ones. LM358, 10 PCs, €1.08 with the postage. The NTC thermistors, €1.03 with the postage. The BD139s, I ordered 20 pieces. I actually need, again, 4 for each one, so that's 12 in total, €2.85. And these little transistors, the 2N5551, in total with the postage €1.36. So you can see the parts are not really expensive. The power transistors cost a little bit, but I will have some spare ones left for other projects. And that's basically all I needed to order. Now, I didn't realise at the time, but I needed the power resistors 0.05 ohms. I've got 4 here that I can use to build the first one, but I need 4 more for each board. So I basically need 8 more of them to actually build the other 2. I had a look around on AliExpress, and although you can get 0.05 ohm power resistors, they were a little bit expensive. So I came up with a cunning plan, or shall we just say, I used Ohm's law. Yeah, and I figured out there was a way to do it cheap. So what I have is these. So you get 10 of them for €1.71. Now, these are 10 watt resistors, and these go down to 0.1 of an ohm. But if we put 2 of them in parallel, we'll have 0.05 of an ohm at 20 watts, which should be more than enough, I would think. Shipping 195, 205. So you're looking at €4 for a pack of 10. That's actually, I need 8 to build each board if I'm using them in pairs. So if I order 2 packs of those, then it'll be 205, €4.05 plus another couple of euros postage, about €6, okay? And that will give me the resistors to build the other ones. But we can build one today and we can test it before we get to build the other 2, and then we can build the entire dummy load into one big unit. Or hopefully one fairly compact unit. Okay, so we have our schematic. I'll get together all the components we need and let's start to build it. I don't have a bill of materials or component list for this, so I've made my own just looking through the schematic, starting with the resistors R1, 2, 3, 4 and so on in order, and I've made a little table. So we have 7812 voltage regulator. R1 is actually a 10k variable resistor. That's this one, which sets the temperature point. That one I think is effectively a little trimmer pot that we just set basically. We have some various resistors, so 100k, 2k, 1k, and for example for the 1k, 5, 6, 7, we need 9 of them. For 70k, 10k, you can see them all. Another variable resistor. This one sets the load current, so that is, I think it's meant to be a multi-turn one. I'll use what I have for now and we can order some of these. These are the power resistors. These 100k resistors, they're not actually marked the component number, so I'll have to see where they actually go. I can look at the board when I build this. Well, I'll figure it out. So those are the 4. I'm pretty sure we have to select by hand, but they may be mounted somewhere else. Why are they in red? I'm sure we can figure it out from the original video. Some capacitors, diodes, a couple of Zeners, and these are the various transistors. And lastly, op 1 and 2, I've classed this as IC1. And ops 3 to 6 are IC2, yeah, because they're all a dual op amp and a quad op amp. Let's start putting one together. So first thing I will do is put all the resistors on the board. It's always best to start with the components which are lowest down and flattest to the board first and work from there. So I'll get all the resistors soldered on and then let's see while we're doing if we can figure out what's happening with these 4. I fitted the resistors basically now. I had a problem in as much as this requires some 2k resistors, quite a few 2k resistors, and also some 200 ohm resistors, and these are not standard values, at least not in the normal, if we can call it, series. So we'd have like 150, 180, 220. Yeah, we wouldn't have 200, so I didn't have any. So what I've done is 2 things. First of all, the 2k resistors, I've made them all using couple of 1k resistors in series, giving 2. So you can see there, here. I've used those. Another one, there's 6 of those. And then the 200s, I've put them together using a pair of 100 ohm resistors. I've also ordered 100 of each for building the others and keeping in stock because they're useful to have. And while I was at it, I ordered 100 10k resistors because I don't have many left. I have a handful of them, so when I get a bit low, I just order some more. I mean, it might be years before I need them, but I'd rather have them in stock than not, yeah? So that's one problem, but that was easy. The other thing is that you'll see here R23. Now, according to the schematic, R23 is a 200 ohm resistor. If you look at another PCB, you'll see we have R23 and we also have R23. So we have 2 R23s. So I fitted all of the 200 ohm resistors made of the 100s in series. We have R33, and if you look down, what we don't have is R25. So we can work this out if we just have a look at our schematic. So it looks like R25 is actually missing, and the easiest way to figure this out is just to measure some resistances. So You can hear the bleep, yeah? So R23, which is here, according to the diagram, goes to the emitter of one of the output transistors, which are these. Yeah, it goes to there, okay? So the other one, which I think is R25, will be the one that goes to here. Yeah, and it is. It's marked as R23, but it's actually R25. And apart from the power resistors, nothing else goes there. So the mistake on the board must quite simply be that marked R23 is R25. So we can get around that problem quite easily. We'll just stick in the correct board, of course. We'll just fit our 200 ohm resistor here. So that should be R25, just silk screen is wrong. So we'll solder this one, and now let's have a look at another little issue that we have. Okay, so just touch these up on here. Okay, so that's sorted that problem out. Now the other thing is that there's space in our board here for R13. There, R13. But if you look at the schematic, we don't have an R13. There isn't any R13. So we've got 10, 11, 12, and 14, 15. Yeah, there's no R13. But it might be that this is the NTC. I think the only way to figure this out is to measure where it goes. So unless I see any other connection on here for the NTC. Oh yes, NTC1 is there, so it's not that. So what's this R13 and where is it supposed to go to? Let's have a look. I might be able to actually see on the PCB where it goes. Well, one end seems to go to, it seems to go to where the fan is. To the fan connection. No, it doesn't go there. Where does that go to? Let me have a look under the magnifier. Okay. Well, that's strange in a way, because R13 in actual fact is the variable resistor. Okay, R13 is there. It's not a mystery at all. R13 is actually the variable resistor. And you can see two pins already connect together. So that's what R13 is. It's just a connection to the variable resistor which goes on the front of the unit. That sets the current, if you like. So R1, which is the 10K, yeah, that goes here. So that's obviously a preset one that goes on the board itself. Looks like one of the little multi-turn ones. I haven't got a multi-turn, but I'm sure I can find something that will fit in there. I'll see if I can use one of these type. I'll order myself a box of these multi-turn trimmer pots. They seem to get used quite a lot in projects. I'm sure on AliExpress I can actually find a complete set of so many of each value, which will be very useful. Let's see if we can bend this thing around. So for now, we can do this. I had the same situation on the milliohm meter as well. I needed really the multi-turn ones. I didn't have, but I managed to use these. So can we get us to actually solder in here? Yeah, with two pins. And the other one probably is a bit too short to reach, but I can extend that and get it to go. Okay, I'll just finish modifying this and we can fit it. Okay, I fitted that in there, made quite a decent job of it, I think. So that's our fan adjustment, if you like. This sets the temperature at which the fan comes on. I can probably use that actually to trigger more than one fan if I'm using the CPU fans, because the CPU fan normally has, you know, one pin to switch it on and off. So I'm sure we can work out how they actually work. these resistors have a habit of bending over and touching each other. I have ordered now some of the 2K and 200 ohm, but for this one it'll do for now. That's all those. So next thing then is going to be the diodes and capacitors. Okay, I fitted the diodes, Zener diodes. It didn't say what they are. These are the 400 milliwatt ones. I have some 1 watt, but I don't have any in 5 or 5.1 volt. I have 5.6 volt, but in the 400 milliwatt I did have 5.1. I've measured them with my LED tester, which measures Zener diodes as well, and they're actually reading 5. This is the 7812 regulator. This is the tip 122. And you know which way round these goes because the thick line there, the double line effectively is the heatsink side. Now this is where we have to be careful because originally I fitted these two, and I realised that when I looked at it, the actual markings show that this one goes an opposite way round to this one. So this has base at this end, this is base this end, this is base this end, and that's back to the base on the other end. So he's obviously done that for layout reasons, but personally I think that's a bit bad. It certainly keeps you on the toes when you're building things. So I've measured this one out with my component test. I'm going to double check this. So this is the one I've fitted here and I've just removed. I had it the same way around as that one. So let's have a look again just to be sure. So we'll use a component tester. We could use a multimeter, but we'll use a component tester. Let's find out which pin is actually the base. So with this you can connect it any way around you like. 3 connections. Okay, and we'll switch it on. It's a good transistor, and red is a collector, blue is the base. So the base is at this end, if you like, the right hand side when I'm looking at the front of it. So we know where the base is to be sure. So this one actually goes in the opposite way round, and the board, they kind of face each other like that. I did have a quick look at the one that the author had built just to check, and he didn't have any heat sinks on the transistor, so I guess they don't need them. Because I've already soldered that one, so I'm actually going to leave that one a moment because the holes have got solder in. I'll try to put a fresh one in here, and then I'll try and fit that one into one of the other spaces. I'm just thinking this might go through the holes a bit easier with them having a bit of solder in. Otherwise, yeah, it looks like I have to just clean them off with a bit of braid actually to make sure they're clean. No problem. Of course, once I've done this, probably they'll both get in anyway, the original one and the other one. But we can just clean this up. So these things sometimes keep you on your toes to actually build them. It's a good job we checked that because we would have had some fun fault finding it afterwards. Okay, so that one goes in that way round. I actually got the one that I originally soldered to go back in once I clean the holes. As you can see, this is coming on quite nicely now. There's not too much to do with it. Mainly is going to be connecting up the output transistors onto the heat sinks and figure out where this switch is supposed to go. Okay, so this one goes in the same way round, which is like so. Okay, goes in the same way round as that one. And then the other one goes in the opposite way round. Yeah. With the heatsink towards the outside end. Actually, I'll just double check these as well. I have known on odd occasion to get particularly MOSFETs, power MOSFETs from AliExpress, that the pinout isn't correct. But if you effectively put them in connected the right way, they work. Can't quite figure out why that is, but I've seen it with some amplifier output ones I say if you kind of like cobble it to get the connections right, it works. And works reliably. Let's have a look just to be sure. So these are the 2N5552. Red is the base. Oh, okay. So red is in the middle. I'll take them as being correct, I think. It'll make for some interesting fault finding if it isn't. Okay. One in there. One in there. Solder those. I found this solder I mentioned before, so it was quite cheap from AliExpress. Yeah, I find it fine. Somebody commented about solder from AliExpress, but this is working. Well, you can see how it's working out. I mean, I'm soldering with it, yeah. This is leaded solder, it's soldering fine. Making nice solder joints, so if you're looking for some cheap leaded solder, this one works well for me. In fact, this is a 50 gram. I've just ordered 2 more 100 gram reels for about €7, like for €4 something. About €4 each, maybe €8 for 2, including postage. Okay, so that's those. Couple of IC sockets, IC holders. Well, there are the IC sockets fitted the right way round again, so there's like a little notch in the socket towards the where it's marked on the board. Little notch, otherwise you just make things very confusing for yourself. I don't see any reason not to fit IC sockets on projects like these. Basically, the likelihood of you making some mistake and damaging the chip compared to the cost of the socket, to me, is just a no-brainer. But again, well, what do you guys think? Fresh day, fresh t-shirt, yeah. I've put most of the components on here, but there are still some things to connect. We have the switch which goes here, which is this switch, which I'm not totally sure exactly what it does. I'm sure we'll figure it out. We have the power resistors, and I don't have the correct type, but I have some of these. Now these are 0.05 ohm resistors. They are salvaged, they're poles, but we can just check to make sure they're good. And I think if I get a stiff piece of wire and put it through here, through the hole, I can effectively put the resistor like so, and then just drop a wire down to the other hole. I'll try that initially and see how they go. So we have those to fit. These clearly go to the power transistors, which are going to be fitted onto the heat sinks, which we'll find in a moment or 5. Power in, that's the power in here. We can connect that to a bench power supply for now. And this connection is to the thermistor, NTC, and it makes sense that that is fitted onto the heatsink together with the output transistors. The thing that's puzzling me with this, another one there, R13, that is the variable, the potentiometer, variable resistor, that sets the current that this will draw. I don't have a multi-turn one, but we can just attach one for now, and then we can have a little play with it. So that's an actual fact is this one, 10K. Great. The other puzzling thing with this, to me, is these resistors, 100K. There's 4 of them, they're marked in red. Now you see they have no component number against them, and there's no place on the PCB for them to go. So you would assume these are external to the PCB. But I had looked through the video, and I can't see, although I might have missed it. I mean, the video's in Russian, sorry, possibly Ukrainian. It's 2.5 hours long, and I put the subtitles on. The translation to English wasn't particularly good, so I kind of looked at the pictures, and I can't see the factors into the heatsink. I don't really see what they are, but we need them. it's possible they're all matched in value. That's a possibility. So I'm going to hand match 4 components. But I can say with confidence that they're not on the PCB. Now, each one, if you look, one end comes from the 12 volt input. Here, yeah. And the other end goes to the inverting input on the op amp, the inverting input. And these 4 op amps are all in one package. This is the LM324. So if we measure from the inverting input to the 12 volt, we should see 100 kilo ohms. That's what we should see. We're not going to see anything through this capacitor, so that will not conduct anything. These transistors are off, so probably we won't see anything coming this way either. So it'll probably look like an open circuit if the resistor isn't in there, and 100k if it is. Let's find out if that's the case. So to do that, we need the pin out for the LM324, which is magically appeared on here. Yeah. So you can see the inverting inputs are on pins 2, pin 6, pin 9, and pin 13. 1, 2, 3, 4 minus. Okay. I'm not sure which input of the op amp is which, but we can pretty well work that out. So we can see each op amp via a 2k resistor goes to one of these BD139s. Yeah. So if we have a look from the output, so the first output is on pin 1 of the chip. And get the meter. Let's see where it goes. It's on a 200 ohms, so I won't use the continuity, but we can have a look. Yeah, so sorry, it's a 2 kilo ohms, not a 200 ohms. We can have a look. So base, well, I can do march on the PCB. This is the base. Doesn't go to that one. Okay, so that one goes to T4. So we know that pin 1 is here. So this inverting input is actually pin 2. We can see where they are. So that's actually pin 2 of the chip. The other input must be pin 3 of the chip. And this is pin 1. So we can just mark on our PCB just so we don't get ourselves too confused any more than I already am somewhat, and possibly you guys are as well with these. Yeah. So the next one is an output. We have one on pin 7. So let's see where that actually goes to. So pin 7 of the op amp goes again to one of these transistors. Doesn't go to that one, quick way you can see it. Doesn't go there. And then these are the way around, so the base is under here. Is it this one, the last one I'm going to? Yeah. Okay, so that pin 7 goes to T5, so it looks like they're in order. So again, we can mark them on our PCB. So this is pin 7. And then the inputs are the negative or inverting input on pin 6. Non-inverting on pin 5. And now do the same for the others, and then we know where they are. We can figure out if these resistors are not there, which I think they're not, and then let's just put some resistors in for now. Yeah, let's just put some resistors in and see what happens. So next op amp is output is on pin 8, which is there. So that again goes to one of these transistors. Where you can see it again. Okay, so pin 8 goes to T7, which is here. So we know that is 8. And then obviously we know what the last one is, yeah. So this is output 3, so 9 is the inverting and 10 is the non-inverting input. And then we don't really need to measure it, but why not? Pin 14. Just to check it, that should go to the base of T6. I'm sure you'll know that it will do. Yeah, it does. So that's 14. Inverting input is on 13. And the non-inverting input's on 12. So we know which pins are which on there. Could be handy if we start troubleshooting this. So, as I mentioned, what's with these 100k resistors? Well, one end goes to the output of the 7812, which is here, which is pin 3. And the other end should go onto this chip, so pin 2. We just measured them all out, we know where they go. Okay, quick way you can see it. So pin 2 on the chip. Okay. It's actually reading about 10 mega ohms, 11, 12 mega ohms. So it's reading actually a very high resistance, but it's certainly more than 100k. If a resistance in the circuit reads more than you expect, then the resistor is bad. Okay, so that's that one, or in our case, just not fitted. Next one goes to pin 6. Well, interesting, that actually reads open. Oh, this now reads open, like something was charged. This is why it reads open. Like something was charging, or like a lead file. I need to get some new leads. So 6. Same sort of thing, well into the mega ohms, so the resistor isn't fitted. And the last ones we know are on 14 and 8. That's the outputs. 13 and 9. Okay. So 9. Same thing. 13. Same thing. So we know that those resistors are not on our board. And we don't know why. So what I'll do is I'll take 4 resistors, I will measure them all on the meter, try and get them as close to 100k as I can, and then I will actually fit them. I'll actually fit them on. I'll solder one end onto these resistors probably if I can. I'll see what's the easiest way to do it. Yeah. Well, let's put those resistors in. These are all the 100k resistors I have, apart from these 4, and these 4 all read exactly 100. So I have 4 that are reading the same as each other, and they're actually reading 100. So we'll use those, and then it's a matter of figuring out how to fit them onto the PCB. I think I might just put them underneath. So one end I can solder to the socket, if you like, of the IC socket to the pins, and the other ends I can just take them all to 12 volts over here. I think 12 volts goes quite a few places on the board. It actually goes to this chip as well. So I think we'll do it that way, and obviously if it's not very tidy we can do it some other way, but I think that's probably the easy way to do it. The other possibility would be to solder it to the ends of these resistors. And I haven't done a PCB, so I can figure out easily which one's which. Let's have a look. Well, what do we have? We have 20, 18, 22, 24. So 20 is there, 24, 20. Yeah, they're all around the chip actually, these resistors here. So I might actually solder one end to the resistor. Just figure out which is the easiest way to do it basically. I've repurposed an old bit of cable, yeah. I take a lot off my scrap ATX cases now. So this is the 10k variable resistor. You see it says B 10k. So A is, if you like, remember, for audio, A for audio, and that's the logarithmic ones, and the B are the linear ones. So I have the linear one, which basically means the resistance changes by an equal amount as you turn it. So a tenth of the rotation is 1k. Every tenth is 1k. Whereas the logarithmic one doesn't work that way. It effectively is much more sensitive at one end than the other, if you like. So one end you're getting small amounts of adjustment, the other end you're getting large amounts. It's used for audio signals. You can go and look it up if you like, but you want a B, okay? switch on there, which I'm still not totally sure what this switch does, but I'm sure we'll find out. So there's a few more things to go. We need to connect the thermistor on some long wires. I have some, we can do that. We need to attach the power resistors, and then we need to attach the power transistors to some sort of heatsink. So I'll get these things put on next. We can just check them because they were pulls, just to make sure they read okay. There we have it. So I've set it to 200 milliohms range. These are 50 milliohm resistors, 0.05 ohms. So we can just clip these on, and let's just make sure they read okay. 51. Go again. Slightly lower. This may cause a little bit of imbalance with the transistors, but I don't know, because each one has its own drive, if you like. These all reading about the same. To about 51, to about 0.47, yeah, 47 milliohms. Okay, so they read, good. So as I said, I'll attach some thick bits of wire, stick them in like this, and then run the wires down from the other side. The modification with the 4 missing resistors, you can see I've fitted them here. So one end goes to the, if I move that out of the way, I'll see a bit clearer. The camera picked up a bit better. So this is one end of the switch, which goes to 12 volts on the schematic. And if we just have a quick look now, we'll just take the meter on ohms range. And if I go from the voltage regulator again, okay, it is here. So the voltage regulator, you can see that connects to here. Okay, and then if we look at these resistors, 100k, 100k, 100.1. Well, this one actually read 100 when I put it in, strangely enough. Okay, but we'll try it. We'll try it. I did match them all originally. I've soldered in the power resistors, so there they are. I've kind of filled the track in with solder, which is a good thing to do when there's very high currents flowing, and I'll do the same with the other tracks when I've fitted the power transistors. So there we have that. Next thing then is to find a couple of suitable heat sinks and figure out how we're going to bolt our power transistors onto them. I have an old PC heatsink here with a copper core in it. It's quite a heavy one, so we can use that. And I have another one, again with a copper core, not the same design but similar, and again quite heavy. So we'll try these two. I'm going to put 2 transistors onto each one. Let's see if we'll fit them. Just have a look. Yeah, they'll fit fine on there. See how the other one goes. I'm guessing it's basically the same size. Let's have a look. Okay. Yep. So we'll put 2 on each one. At the moment they can stand on these little legs, so these will be underneath. I'll use some heavy gauge wire to attach them to the PCB. So that will do for that. I have a fan output on here. I'm not sure if I'm actually going to use that, but I think I will just attach a fan. We can probably use that just to keep these cool actually. And the idea is that I can actually mount the PCB between the 2 heat sinks like so, or maybe even find 2 matching ones if I really want to do. Yeah, something like that. Each of these then, if this is capable of the power it says, which is 300 watts, each one will be dissipating at maximum 150 watts. And given the fact these are used on some high powered CPUs, they can probably do that. That's my theory, but we will see. Okay, so that's how they're going to go. I'll drill some holes into these and I'll get these mounted on. That shouldn't be too difficult, and then I'll put the last bits of this together and then let's see if it actually works. There you have it guys, I've put it together. So I have 2 transistors on each heatsink. One of the things I discovered while doing this is that copper is not the easiest thing to drill, at least not with the tools I had. It has a nasty habit of clogging up the drill bit. The first hole I put in, I actually then managed to snap a self-tapping screw off and couldn't get it back out, so I drilled some more. I broke at least 1 drill bit, and they just have a bad habit of clogging up basically. But anyway, I have it done. I have the ICs inserted. So obviously we have the fans on here. At the moment I'm just going to connect one of the fans just to try it. So these are 3-pin fans. You can use these quite easily. I'll just put my power supply on, 12 volts. I will show you. So basically with these, the red and black are the power, and the other lead, whether it's yellow or blue, whatever colour it is a speed control. So if I just tilt this one up a little bit, that'll turn it over, and we can just go between the positive to the red. I have the power supply on 12 volts, and the theory is that the fan should rotate. So I can power the fan up. I'll sort out wiring them both later once I've actually managed to test this, but for now I've put a little pin header on here so I can connect my fan, positive, negative. Okay, at least we can prove whether the temperature thing actually switches the fan. This is the little NTC thermistor. For want of a better idea, I'm actually going to stick it up inside here. I think I might actually just put a little bit of, if I can find it, heatsink compound on it. Yeah, just to get a little bit of this on it. I've put a heatsink compound on the transistors. Put a little blob on there just to help the conduction. Okay, and then this can actually just go up inside here. I can only monitor the temperature on one anyway with the circuit as it is, but with a bit of experimentation using the thermal camera or just a thermometer, I can figure out, you know, which one gets hotter than the other, being slightly different designs. And having the thermistor in one should quite easily protect both. So we have that. I have a potentiometer, as I mentioned before, 10k. I've just soldered a pin header on again, one I took off an old ATX. Well, old ATX case actually, yeah. So somewhere that goes in here, which is marked as R13 as I remember it. Yeah, that goes on there. So we have that. Well, we have the switch, which I'm not totally sure what it does, but it looks like it switches the power here from either the incoming 12 volts or from the voltage we are using to test. So I think the idea of this is so that you can actually power the dummy load, or active load as it is, from the actual device power supply under test. But for now I'm going to power it from its own separate power supply. So we can attach the switch again on a little pin header. This connection is for my load, so I'm going to use my 10 amp power supply. I'm going to load it, and this connection is for the power, and for now I'm going to power it from my other power supply, one of my other power supplies, to test it. Put 15 volts in as it suggests here, 15 to 24. I'll stick 16 in, and then we can try it. There's a switch going on. Definitely a header for it somewhere, because I remember I soldered it on here. Yeah, there it goes. Okay, so that's our switch attached. That's about everything we need, really. We'll soon figure out which way the switch goes, because I'll actually connect it to my bench power supply first. There are the two bench power supplies. This one's a 30 volt 5 amp, this one's a 30 volt 10 amp. So we're going to use this one to power the project, and this one as the victim. We're going to use that to load. So first of all, let's power the project. Let's power on here. I'll just turn the current down quite low, just in case anything bad happens. In fact, we could just check, actually, if I just short the power supply leads. Yeah, it's set to 0.8 of an amp, that's been more than enough to power this. So DC in, what have we got? Well, it's drawing practically no current, you might expect. Let's try flick the switch. Okay, now it's drawing 20 milliamps, so we know it's actually powered up. The next thing we'll do then is attach the power supply, which we are going to load. I'm not totally sure what load this is going to present, but I think if we turn this up to the maximum resistance, do you know, actually, I don't know which way it goes round. Let's put it to the middle. Yeah, let's put it to the middle just to see. So we'll put that in the middle. That sets the load current. We'll switch this one on. Now, obviously, this has a current limit on it, so I'll put this to 12 volts. Let's simulate testing a 12 volt power supply. And let's just set it first to quite a low current anyway, just in case something bad wants to happen. Yeah, so we'll just put these on here, tighten this up a little bit. We'll turn the ampage down, so it's quite low at the moment. Let's short this one together, okay? I'll give it, well, 2.75 amps, yeah. Let's attach our power supply and put a load on it. So this goes on here, load, negative, positive. This might well now cause this to go to constant current mode because I don't know how much of a load I've set it to. Well, that's if it's going to constant current mode, yeah. So I'm going to turn this down. Ah, and it's working. It's working, but the control's working backwards. Look, I can turn the load up, and eventually it trips the constant current on the power supply, yeah. So we'll turn the current up on here, and we'll try to put a load on it. Yeah. These feel cold at the moment. Let's just put the load up. About 9 amps. That's warmish. That one's still is warming up a little bit. Turn it down a bit. We can get a thermal camera, you'll see what it's doing. Okay, so we can see it's working, but straight away I see I actually have a problem with this. These three devices you can see lit up here quite bright and red. If I just get some focus. These are the driver transistors, but only 3 of them have actually warmed. The fourth one, which is here, it's there, is actually cold. So on this heatsink, one of the transistors is, I mean, it's not hot because I have it on a low current. In fact, I can't even feel the difference, but you can see. I've put the little graticule on now. Something's making a noise. Can you hear that? I don't know what's making the noise, but I think it's this thing. Okay, go to this one. The fans are not spinning. But this one you can see both transistors are getting warm as you would expect, yeah? And this one only one. I don't know where that sound's coming from. Let me have a listen. It's something on my circuit board that's making the noise. Stopped again. Back again. Okay, well let's see if we can figure out why this transistor here is cold. That's the first problem. Why have we got one transistor not working? Right, I figured out what the noise is. The fan had seized up. something was stuck in it. So that's what the noise was. It's the fan. So the fan has come on. That's a good sign. So that much works. Now, why have we got a problem with it? So let's have a look at the voltages around these transistors. I'll try and make a little bit of space so you can actually see what we have, okay? Well, the easiest place to test probably is actually on the output transistors. Let's see what we've got. So I'll get onto ground, find a decent ground. Yeah, probably just where the lead's coming in actually. This one. I'll use a crocodile clip. Okay, I have a ground on my test meter. Now, what we got? So, base. What's 0? Collector should be 12 volts and the emitter should be 0. So this transistor is off. The next one, base is 0.679. So this transistor is on. This is 12. This is ground. So that's why one transistor is just fractionally warm because the low current, the other one is off. So the problem is that we don't have any base voltage on this transistor. If we just look at the other ones, that one is on, okay, and this one is on, and both of those are just tepidly warm. Which of the transistors is driving it? So whichever one it is, if there's nothing on the base, one of the transistors, the drivers, is not being turned on. That's fairly obvious. Let's have a look. Emitter of this one, 0. Yeah, I'll find one of the other ones I can easily get to. This one should be working. 0.677. So this transistor is not turned on. Okay. If it's not turned on, then either it's open circuit base emitter or it has no base drive, whichever one it is. So let's have a look. So base of the transistor is at the other end. I'll just get to it. Very low, yeah, 0.025. Whereas if we look at a good one, this is a back to front one, it's easy to get to. The base of that one has 1.3 volts, yeah. Base of this one, about 1.3 volts, yeah. So all the other ones, just get to this one, 1.3 volts. So this transistor has no base drive. Now the base, if we look, comes via a 2K resistor from one of the op amp outputs. So we mark them all so we know which is which. So 1, 7, 14 and 8 on this chip. Yeah, so let's have a look what we've got. These are the outputs. Well, 1 has 10 volts on, yeah. 7 has only 1.3 on. That has 1.3 on. That has 1.3 on. So there's something wrong here, yeah. There's 10 volts on pin 1 of here. Okay. Is it by chance this resistor's open? Because we have 10 volts on here, but I'm guessing, well, in fact I don't need to guess. Pin 1 goes to T4. And T4 is the one that isn't working. And the base of T4 has, we get to it again, practically 0 on it. It's a bit awkward to get down there, but get in from one angle or another. Otherwise I just turn it upside down. Let me see if I can get at it. Well, actually I don't need to get directly at it. I can get to the end of R26. Yeah, R26 goes between the two, which is R26. This one. So this end has practically 0. Other end, no, that's R28, sorry, that's not R26. Let me find R26. do it the easy way, I have another PCB. Okay. R26 is the one in front of T4. It's there. This is it. So that end has practically 0, and the other end practically 0. Is there something wrong here, like an open circuit? I mean, we know pin 1 of here has well, actually now it has 1.3 volts, so I wonder if I had a bad connection. Yeah. They all have 1.3 on now. I bet they're all working now. I think I just have a bad connection there. Well, strangely enough, no, I still only have 3 of the transistors warming up. This one is cold. Have another look. Let's have a look around it again. So, output from the op amp is back to 10.72, and down to 1. Yeah, I've got a dodgy connection down somewhere on this resistor. Can you see? As soon as I touched it, it went back to how it should be. Is it working now? Yeah, all 4 are lit up now. Okay, so I just have an intermittent connection on the resistor there. Yeah, I'll hold it like this. It's a bit easier for you to see now. So we now have both output transistors warm on this heatsink, and we have the same on this heatsink. Okay, so that's just a bad connection on that resistor. I can soon fix that. Let's give it a little bit more current now so we can increase the load. I've got this wired back to front, but I can fix that. So we've now hit 10 amps. And then it tripped out on my bench power supply, you see it. Okay. 10 amps, and then it trips out the power supply. So I won't run it at its full power at the moment because I only have 1 fan connected. But these are not overly hot. If you can see the temperature of them. Put the little thing on. But they're not overly hot. Yeah, 39, 35 degrees. Let me turn the current up again. So I've got about 9 amps there at the moment. Yeah. Okay, it's now running at 70 degrees. So definitely needs the fans running. This one is, yeah, a bit cooler than this one. I can feel that. So I think we can agree as a basic first test it does work. I'll just show you now what I have in mind for this project to complete it. Somebody gave me this for free actually. I spotted it at the car boot sale one week and didn't buy it. It disappeared, and then a few weeks later somebody gave it to me. Said they'd bought it but didn't know what it was. So this is actually an old automatic voltage regulator. The idea of this is that if the 220 volt mains is unstable or 110 volt, it can regulate the voltage. And the way it does it is this thing. So this, if you like, is a variac. So you see the slider moves across the transformer, okay? And if you like, it's like a variable transformer, okay? And this side has a little motor that drives it and a little control board. And when I first saw this, I thought, hey, I can make a variac out of this. So if I effectively modify the circuit a little bit, put a potentiometer on the front of it, I can get it to drive the variac to whatever position I want it to do. And I've got a variable power supply, 0 to 220 volts AC. Unfortunately, it doesn't work like that. This variac can only alter the voltage by about plus minus 30 or 40 volts. It doesn't give you the full range of voltage, so it's no use for that. But what I do have is a rather nice case. I think, but I'll have to experiment a bit. I can probably fit, yes I can, both of these heat sinks in, yeah, possibly on that side. So what I would like to do with this is to build a triple channel load. So effectively make 3 of these, okay. This one I'll have the 2 heat sinks on and they'll probably fit into the back there. The board can go in here somewhere. And then the other 2 I'll actually put all the transistors onto single heat sinks. And the idea is that one of the power supplies can handle a very heavy load, another one's for lighter load. So I can load an ATX power supply, for example. I can put the main load, this lot with the 2 heat sinks, onto the 12 volt, and then use the 2 smaller ones to load the 3.3 and 5 volts because they have less current capability, and also because the lower voltage, the wattage is lower. Yeah, watts is volts times amps. So I have some heat sinks like this one, old P4 heat sinks, that can actually fit 4 transistors on there. And if I have the space, I can do something like that. If I don't, I can find a different cabinet. Nice thing with this one is that the front panel actually comes off with a couple of screws here. So I can take this off and I can effectively put maybe a piece of plastic across the front of it and then put the holes where I want them to go. So that's what I have in mind. I'm also thinking of adding some voltage and amp meters. So I have a few like this one, volts and amps, and I have some current shunts to go with them. So these can handle up to about 50 amps. So I think what I would like to do is to put 3 displays on the front for the different voltages, put shunts in there, so on the front of it you can actually see wherever I decide to fit them, that is, maybe down here. In these spaces you can actually read the supply voltage from the power supplies you're testing, fit on here ATX type socket, and maybe some terminal blocks, jack sockets if you like, 4mm type banana sockets, so that I can use as a general load. So a lot will depend on how much space I have. These are not going to be too big, so I'll experiment with this a bit. So you will definitely see a part 2 to this when I actually build the complete thing, the triple channel tester. I'll be interested to hear your thoughts on that. Another possibility, because of high wattage, would be to use something like this. I have several of these taken from scrap graphics cards, so again I could fit the power transistors on here, attach the fan, and maybe put either down the side of this or use something else. So lots of ways that this can be implemented, but from what I've tried with this, I'm quite confident if we can get enough cooling on it, this will actually dissipate the 300 watts. There is one other thing I'll just mention, and that is with this circuit. So it should be quite simple, I think, with this to actually effectively have 8 output stages if you really wanted to. So effectively duplicate all this, because I have several of the PCBs. I have 2 PCBs together, one driver circuit driving both boards, so I'd have 8 pairs of transistors on the output. I mean, the only connections coming in, as you can see, are the 12 volts onto these 100k resistors, the connection from this op amp, and that's really about it. There isn't really any other connection that I can see between the 2 sides of the circuit, so I don't see any reason why we couldn't do something like that, actually. You can see then we have the good basis here for a triple channel active load. We have lots of scrap stuff we can use. We have 5 of these PCBs and they are quite inexpensive to construct each one. I have lots of these types of coolers. I have one possible cabinet to fit it in, but it might not be big enough. I'm sure I can find something else if it isn't. So there's lots to play with here. I need to order the power resistors to build the other ones, so that's going to take a few weeks from AliExpress. And I'm still interested to know what was what with these resistors. I would just like to say thank you again to PCBWay for sponsoring this channel and giving me the opportunity to build things like this, nice pieces of test equipment which we can make at low costs, much cheaper than buying an item to do this. And I'd like to thank you guys for watching, because without you guys watching this, I also wouldn't be able to do this sort of video. Yeah, I hope you enjoyed that as much as I enjoy building it, and I hope you'd like to make some suggestions about the construction of it, how we can get the highest wattage dissipation out of it, what you think about the addition of the current and voltage meters with the shunts, and whether you think we can get at least 300 watts out of this load. Yeah, can we get up to 30 volts, 10 amps, and it not overheat or blow up? Yeah, I'm sure we can expand this. We can have 4 of these with 1 transistor on each one. There's lots of things we can do. We just need the space and the enclosure to do it, and if this one isn't big enough, we can find something else, I'm sure. Okay, let's hear from you in the comments below, and I will see you all soon on another Learn Electronics Repair video. Ciao for now, guys.